Okay, this is our lesson on two-dimensional motion, and we're looking at the key thing here is that horizontal motion and vertical motion are completely independent of each other. What does that mean? So think back to our lab as we did this. This means that the acceleration due to gravity doesn't affect the horizontal motion of an object. And the opposite is true. The horizontal motion of an object doesn't affect the acceleration due to gravity. If I throw an object horizontally as I drop one from the same height, they would hit the ground at the same time. The only difference being is that the one with horizontal motion would have a greater displacement in the horizontal direction. So in our lab we saw this when we dropped a pumpkin in a tank shell, and then we launched it horizontally from the same height. So it always took the same amount of time to reach the ground if we take air resistance off. And so when we look at this, we're going to be thinking about the horizontal motion and then the vertical acceleration. The vertical acceleration is due to gravity, so we give that a specific value of g, which is a vector, of 10 meters per second squared. That means that after 1 second, an object that's dropped from rest goes from 0 to 10 meters per second. At 2 seconds, it'd be going 20 meters per second. At 3 seconds, 30 meters per second, and so on. And again, this is not accounting for acceleration due to gravity. So let's take a look at what this means in terms of our lab, and then we'll look at how to break up this motion when we have horizontal and vertical motion into vector components, which just means how do I take that arrow that shows the velocity going down to the right and break it up into the horizontal x component and the vertical y component with two separate arrows. Okay, so here we have our cannon being launched from 10 meters. We're going to look at an initial speed of 0 meters per second. So that's the horizontal speed. So that means essentially we're just dropping the cannonball. And we want to see how long it takes to hit the ground. And we want to be able to compare that to how long it would take to hit the ground if we launched with the speed. So there it just dropped to the ground. It took us 1.43 seconds for it to hit the ground. Now, we're going to compare that to giving it a horizontal velocity and see how long it takes to hit the ground. So now it's at 5 meters per second. Let's take a look here to see how long it takes to hit the ground now. So we launched it. You can see those two arrows are its vectors, and 1.43 seconds remains the case. So that horizontal speed of 5 meters per second didn't affect how long it took to hit the ground. So it's still accelerated to the ground at the same rate. And that's what we mean that they're independent. That motion, that velocity I gave it, didn't affect it. Let's try again just to see it 10 meters per second. Very similar to what we did in our lab. So we launch it now, hit the target that time. Let's see how long it took to hit the ground. What do you think it's going to be? 1.43 seconds. Now the difference is just how far it went. The range there represents how far it went horizontally. So we had 1.43 seconds for it to move to the right. And when it's going faster, you take that 1.43 and multiply it by 10. So it went 14.3, or just under that, 14.28 meters. But what we see here is that horizontal motion didn't affect how long it took to hit the ground. And that's what we call independence of horizontal and vertical motion. Take a look at that motion with the motion to the right and the motion headed downward, and breaking it up into those velocity vectors. So we know that as it moves, you can see that arrow to the right represents 10 meters per second to the right. The arrow down is getting larger because it's accelerating towards the ground. So what we want to do is investigate that arrow down. What's going to happen as this goes further along to those two arrows? Well, let's run the video forward here a little bit, and we can see that arrow down is getting larger and larger. The arrow to the right remains the same. And again, that's another component of the independence of horizontal and vertical motion. That arrow to the right, horizontal motion, we have constant motion horizontally. It's 10 meters per second. Downward, we're accelerating. So my acceleration is all towards the ground. So we're going to look at how we combine those two vectors to show its velocity. And we call this the tip-to-tail method. So let's take those vectors, and I have them here in Notability just so I can draw them up and edit them. And I'm going to go ahead and circle those two and copy those. I'm going to bring them over here to the right, and we're going to take a look at what happens to combine those. So those are now broken up into their components, vertical and horizontal. I'm dragging that vertical. The tip-to-tail method means take one of the components and start its tip its tail at the tip of the second. So I took the horizontal component, and then I started the vertical component, or the downward arrow, right where that horizontal arrow ended. And now I make one arrow from the beginning to the end. And let's straighten that arrow out. And that arrow represents the actual velocity. So my velocity is downwards to the right. And that's what we call combining a vector. Moving the other way, if I had that downward to the right arrow and split it up into those two green arrows, then that would be splitting up a velocity into its horizontal and vertical components. And we can look over here, drag it back on the picture, and we can see that that red arrow represents the velocity at the instantaneous velocity, which means the velocity at that given moment. Now, as we go further along, that downward arrow is going to get larger. So what's going to happen to that red arrow? Think about it. Well, if that downward arrow gets bigger, as we see here, and then we take those two vectors, so that downward arrow, you can see that when it's highlighted, it's larger. We take those two arrows and we combine them to find the instantaneous velocity. What's going to happen now to our resulting vector, or the red arrow that we had? So we'll take that downward arrow, we'll put it where the tip of the horizontal component ends, and then we will take that red arrow from above, and we'll go ahead and see there was our original one. We can see it tilted further downward to the right, and that's because as an object accelerates, we get that parabolic, or that curve downward, where it gets steeper as it goes. So as time goes on, the velocity becomes more and more downward, but notice that the horizontal component stays the same, and that's that independence of horizontal and vertical motion. Okay, so now let's see what happens if we fire it from an angle. So we have an angle here of 45 degrees. We have a height of 0 meters. So we're looking at breaking up our velocity into components again. So now when we fire the cannon, think about it. What is our horizontal and vertical component? Well, the horizontal will remain the same, but look at the difference is that at the start of it, we already have a velocity that's upward to the right. So we're breaking that up into its components to the right and upward. And as I launch it, that up arrow is getting smaller and smaller, because remember, it's always accelerating towards the ground until we get to this top point where momentarily it doesn't have any upwards or downwards velocity, all the motion's to the right. Keep in mind that's its instantaneous velocity, so it's still accelerating towards the ground. So what's going to happen next? Well, that right arrow is staying the same, the downward arrow gets a little bit larger, and then let's see what happens as we go further on. That downward arrow is getting larger and larger. When we combine those two, we're getting a steeper and steeper downward velocity, which leads to that curve, or that parabolic trajectory we see there. Now let's break those up into components. So here we have the initial velocity. Those are those two arrows you saw, upwards and to the right. When we paste those over here and combine them, remember, we're going to take one of the components and start the arrow where so we're starting that vertical arrow where the horizontal component ends. We take another arrow and we go from the start of our horizontal to the end of the vertical, and that represents its instantaneous velocity, or the velocity at that point. And all we're doing is breaking that up into horizontal and vertical, because that'll let us do things like calculate how long it's going to take to hit the ground, because that right arrow is not going to change. The only one that's going to change is that upward arrow. And again, we call this breaking up a vector into its components, horizontal and vertical. Now we're a little further along. Remember, it's accelerating towards the ground, which is opposite the direction of its vertical velocity there. So that arrow upwards got smaller. What's going to happen to our resulting vector? Well, let's start at the beginning of the horizontal component, end at the vertical component, and we can see that we have a little bit less steep of an instantaneous velocity. Keep in mind that horizontal velocity is the same, because it's not affected by that acceleration due to gravity. So again, this is the key component of looking at breaking up a velocity into its vector components. In this case, that's at the very top of its path. We have a velocity, it's all to the right. So what is that going to result in? Well, I have no other arrow, so my resulting velocity is just the same as that horizontal velocity. At that moment, the instantaneous velocity is completely horizontal, because its vertical velocity is 0 meters per second. Remember what happens after that moment? That the cannonball continues to accelerate towards the ground, so I'm going to have velocity pointing downwards. And now, what's going to be my resulting vector? That over to the right, and then we can see that the resulting vector is downwards to the right. What's going to happen as it falls further towards the ground? Which one of those arrows will change? Which one will not? Well, think about the direction of the acceleration. Gravity is always pointing downwards to the center of the Earth. So we can see that downward arrow got larger. What is that going to do to the direction of my arrow? That resulting vector, I should say, the red one? Well, it's going to be a steeper to the right. So the key ideas I want you to take away from this are that the horizontal motion does not affect how fast an object accelerates towards the ground, and that we can break up velocity or any vector at an angle into horizontal and vertical components using this visual tip-to-tail method.